Collaborative Filtering Using 5 Algorithms by Kristin, Mark, Adriana, and Eli. Our project was to create a recommendation engine for restaurants, meaning that we used the type of restaurants a person has liked in the past to predict the ones that they might like in the future. To do this, we use basic user, item, and content-based collaborative filtering, along with naive-based probabilistic and k-means clustering algorithms to predict users' ratings of restaurants. We used data from Yelp.com, and from this, we created a suitable subset of around 4,000 users, 40,000 reviews, and 3,000 restaurants from the original extremely large dataset. So what exactly is collaborative filtering? Let's try an example. This is you. See the rainbow cake that you're eating? Why did you decide to eat rainbow cake instead of chocolate or vanilla? Maybe you heard about it from a friend, or your Aunt Sally, or your professor, the internet, or your mom. But what if you couldn't ask these people what types of cake would be good to try? How would you know what you should try next? Collaborative filtering is a method of making automatic predictions about the interests of a user by collecting preferences or taste information from many other users. In other words, using the cake you've liked in the past to predict the cake you'd like in the future, based on what people are in similar taste in cake like. So there are three main types of collaborative filtering: user, item, and content-based. Let's start with user-based. Let's say that you ask people similar to you what types of books they like to read, for example. And they say that they all like Game of Thrones. So maybe you'll also like Game of Thrones. Whereas item-based says that you know that you like, for example, the 7th Harry Potter book. Whereas other people who like the 7th Harry Potter book also like Game of Thrones. So maybe you'll like Game of Thrones. Whereas another approach is content-based, where you know that you like books that have fantasy, drama, and suspense, maybe like the 7th Harry Potter book. But Game of Thrones also has fantasy, drama, and suspense. So maybe you'll also like Game of Thrones. Naive Bayes and k-means are very different. Naive Bayes uses conditional probabilities from groups of similar users in order to predict ratings. And k-means creates these clusters for naive Bayes to work on. How k-means work is it starts with a set of data and creates a set of means arbitrarily. It then clusters the data into however many clusters you wanted, then calculates the average of the new clusters, and then those become another set of new clusters. And it does this until the algorithm converges. So how do we actually implement these collaborative filtering algorithms? As we were able to combine user and item-based into one file, which I will run now, whereas content-based, it works, but we weren't able to integrate it successfully into these other two. The calculation for content-based is rather cumbersome, so we won't subject you to watching that. But when this is done, we expect to get a table like this, where you can see that we have some user, let's call him Fred, and some restaurant, let's call it the Border Cafe. And we know that Fred, in real life, visited the Border Cafe and gave it 4 stars, because this is in the original Yelp database, and we pulled out this data point so that we would be able to use our algorithms to predict how much Fred likes the nachos in the Border Cafe. So using user-based collaborative filtering, we predicted that Fred would not really like the Border Cafe, and the same with item-based. So that one, a little bit off. But if you look down these lists, you can see that some of them are actually pretty close. Like this one right here is only 0.3 apart, and this other one right here is only 0.2 apart for user-based, and even closer, it's only 0.7 apart for item-based. And see, we have our output right here. But how do you quantify error in something more than, oh, that's really close? We decided to plot the absolute error of our user, item, and content-based collaborative filtering. So if you look at this, you can see that most lie within plus or minus 2 from what they were expected to be, which seems reasonable considering our stars only range from 0 to 5. And looking at this plot, you would expect that if your prediction perfectly matched the actual rating, that this dot would line up on the axis. You can see that we have a couple of really good points as long as a couple of terrible points. We also did this type of plotting for combining user and item, combining user and content, and combining item and content. Unfortunately, this didn't look like it gave us much of a gain. But how do you quantify looks like, once again? A very popular error metric is called the root mean square error. So we calculated that for all combinations of our data sets and found that overall, content-based alone is the best predictor of correctness, whereas item and user should not be trusted with anything. Various combinations scored in between, but content was the clear winner.